Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatru from the Department of Physics and Astrophysics, University of Delhi, Delhi, India. Today we are going to discuss about the module Auger Electron Microscopy Part 2, which is coming in the spectroscopic methods from the paper Characterization Techniques for Materials 2. From this module, students may get to know about the following. First is the peak identification, chemical shift and quantitative analysis of Auger electron spectroscopy, and the depth profile of this Auger electron spectroscopy will be discussed. The secondary electron emitted due to the incident electron beam produces a vacancy in the lower energy level, usually the K cell. This vacancy can be filled by an electron from an outer shell with higher energy, and appears to two possibilities when an electron with the high energy fills this vacancy. First, it can emit the X-rays through radioactive process, or second, it can emit an electron through a non-radioactive process, generally termed as Auger electron. The Auger electron is produced by the knocking out of an electron in higher energy level by radiating energy when the vacant space is filled by an electron with higher energy. Auger spectra is expressed in two different modes, the direct mode and the differential mode. A typical direct mode AES spectrum is a plot of intensity versus kinetic energy. The signals from Auger electrons are relatively weak compared to the secondary electrons escaped from a solid surface, resulting the Auger peaks appear small in the background of direct mode spectrum. Generally, differential mode spectrum produces the first derivative of intensity using computer software and plotted versus the kinetic energy. The differential mode spectrum is effectively reduce the background noise and enhances the signal to noise ratio, resulting distinct Auger peaks. The AES is a powerful tool for surface chemical analysis. It can identify the chemical elements in the specimen layer within a range of several nanometers from the surface. Importantly, the peak positions of elements formed in XPS and AES spectra are sensitive to their chemical nature. For example, the positions of carbon peaks in carbon dioxide are different from the appearance of the peaks in the saturated hydrocarbons. This phenomena is referred as the chemical shift AES spectra and provides extra information for the chemical analysis. The AES instrument is capable of generating depth profiles of the surface layer going towards the inner layers of bulk materials and reveal the spectral distributions of elements on the surface of bulk material. The spectrum analysis. The concentric hemispherical analyzer represented as CHA of the Auger electron spectroscopy has a resolution for energy delta E divided by E over the whole range of the spectrum. The direct mode spectrum is expressed the energy distribution as the number of electrons times its kinetic energy, which is E NE. The differential mode spectrum is represented by E times dNE as the axis parameter. The Auger energy in the differential mode is represented by a sharp peak or dip position corresponding to an Auger signal. Figure 1 shows the energy of carbon KLL line in the differential mode is 272 electron volt and the equivalent carbon KLL peak energy in the direct mode is positioned in higher side because the exact peak energy is the differentiated curve passing the 0 in the axis. This difference is ignored during analysis for elemental identification. Qualitative analysis of the AES includes identifying elements from the location of the peaks in the energy spectrum. The light elements are identified from the dominated KLL Auger lines in the spectrum range. For elements of atomic number higher than 15, either L, MM or MNN Auger lines dominate the spectrum. The principal Auger electron energies for different elements are represented in figure 2. The dotted red lines indicate stronger and most characteristic peaks. The LMM lines are divided into triplets resulting from the differences in subcells involved in the Auger process. The peak identification. Qualitatively, the analysis for identifying the peaks in AES spectra is started by comparing the peaks appear in the experimental measurements with the standard peaks found in references books as given by as represented in figure 2 or computer databases. Two different X-ray sources can be used to distinguish between the Auger peaks and XPS peaks. The change in kinetic energy of an Auger electron with energy of primary X-rays is represented by the Auger peak. Thus, an Auger peak shifts in apparent binding energy in an XPS spectrum when we change the X-ray source. For example, an Auger peak shifts by 233 electron volt in the XPS spectrum by changing the radiation from magnesium K alpha line, which is 1253.6 electron volt, to an aluminum K alpha line of energy 1486.6 electron volt. Chemical shifts. Chemical shifts also occur in AES spectra, and the chemical shifts can be significantly larger than the shifts in XPS. For example, the shift between aluminum oxide and aluminum metal peak of Al Kl2 Kl3 is greater than 5 electron volt, while the corresponding shift of Al2p binding energy is only about 1 electron volt. In addition, Auger peak shape may be affected by the chemical state. Also, the position and shape of oxygen KLL Auger peaks in different types of oxides is shown in figure 3. The OKL1 L23 and OKL23 L23 peaks from the oxygen vary in separation by up to 5 electron volt, and the shape of the OKL23 L23 peak can be singlet or a doublet type. The comparison of positions and shape of oxygen KLL Auger peaks in several solids is represented in figure 3. Now let us see what are the different issues with insulating materials. In insulating materials, it is difficult to remove the incident electrons on the surface of the material by pursuing electrical conduction methods through the material. This causes accumulation of electrons, and the sample surfaces of the sample becomes negatively charged during the Auger electron spectroscopy. This accumulation of charges change the surface potential and further affects the detection process, and the measured kinetic energy or binding energy could change by tens of electron volt compared to the already published table database. It is difficult to overcome the surface charge problem with insulating samples for AES, as the electrons have to be removed from the insulating surface rather than compensating for electron loss. AES does not work well with fully insulating materials. Generally, the methods used in AES for reducing the surface charging problems are: first, by reducing the primary electron beam energy. For example, the surface potential can be stabilized when the energy of the primary electron beam is reduced and changes from 10 kilo electron volt to about 2 to 5 kilo electron volt. Second, making use of a conductive coating on the sample's surface. Coating the surface of the specimen with a thin layer of metal such as silver or gold to increase the conductivity to move the accumulators electronic charges near the area to be examined. The quantitative analysis. The quantitative elemental analysis of electron spectroscopy and X-ray spectroscopy are almost similar to each other. The AES measures the intensities of the peaks and quantifies the concentrations of chemical elements on the surface of the sample. Most of the parameters required for estimation are not available in both the XPS and AES. Quantitatively, the atomic fraction of elements can be estimated theoretically from the intensities of electron signals by following the mathematical expression Xi is equal to II divided by Si whole divided by sum over Ij divided by Sj, where Xi is the atomic fraction of a surface element, II is the specific peak intensity to be quantified, and S1 and S and Si and Sj are the sensitivity factors that can be determined experimentally for every element and varies according to the instrument and surface of the specimen. Generally, the sensitivity factors are taken from the published handbooks with certain corrections according to the instrument characteristics. As it is not feasible to compile a set of in-house sensitive factors, the intensities of XPS peaks is evaluated from the peak areas after subtracting the background and the chemical contamination on the surface of the sample affects the accuracy of equation 1. The quantitative estimation using this equation is based on few assumptions and approximations. Cautions need to be exercised during calculations to prevent erroneous results. The intensity of AES peaks is considered as the peak-to-peak height in differential spectra. However, the peak-to-peak heights depend on the instrument resolution and the differentiation or modulation processes using computer software. This problem may be resolved by using the AES direct spectrum. The presence of chemical contamination on a surface of the sample affects the accuracy of using equation 1. For an AES spectrum, the matrix composition affects the efficiency of the Auger emissions because the backscattered electrons in the matrix also excite the Auger electron emission. Here, the intensity of the element A present among multiple elements differs from the same amount of A element in its pure solid form. The composition depth profile. The compositional changes with distance from the surface plane can be characterized with Auger electron spectroscopy. The most common method for measuring a depth profile of composition is through spotter depth profiling using an ion gun. The ion gun can produce a flux of positively charged argon ions with current density and energy in the range of 1 to 50 microamps per millimeter square and 0.5 to kiloelectron volt respectively. The atoms are ejected from surface of the sample by bombarding ion beams and by rastering ion beams directed at the surface and develops crater. A profile of the compositions at the surface and near the surface could be known by examining the evolution of the AES and XPS spectra of through the crater at different depths. For analyzing the depth profile quantitatively, it needs to measure the depth very accurately in addition to estimate the concentrations. Several factors need to be taken into consideration for analyzing the resolution of depth measurement, including the following two factors. First, the etching rate for every atom is not constant for identical ion beam energy and ion densities. Thus, the preferential etching occurs for samples containing multiple elements. In samples comprising of several elements that are not uniformly distributed, certain areas would be etched faster than others depending on the preferential etching. This results a rough crater surface, and increasing depth of etching could produce much great structure. Here, the depth scale of the profile is based on the average etching rate and the measured concentration of elements with higher etching rates provide higher spotter yield, which would be higher than the exact concentration of the specimen. Secondly, the incident ions can smear the interface during the depth profiling. Figure 4 represents the schematic diagram of the interface smearing during depth profiling. When an ion beam gets bombarded onto the surface of thin film sample with a smooth interface with the substrate, the depth profile of element A often exhibits diffusion rather than sharp interface profile expected to be for the real case. So students, let us summarize what we have learned in this module. We learned about the typical Auger electron spectroscopic methods, and the spectrum is a plot of intensity versus kinetic energy, and it is a plot of the first derivative of intensity versus kinetic energy. The spectrum analysis, peak identification, chemical shift of AES spectrum, and problems with insulating samples are studied with schematic diagrams. The quantitative analysis of AES and sensitivity calculation has been discussed. This quantifies the concentrations of chemical elements on a sample surface from the peak intensity of the spectra. In theory, the quantitative relationship between the intensity of electron signals and atomic fractions of elements can also be calculated. The AES can analyze the composition changes. The most commonly used method to obtain a depth profile of composition is spotter depth profiling using an ion gun. Thank you.